for our last talk today. We're happy to have Luya Wang, who will tell us about deformation in equivalent symplectic structures and Donaldson's 4-6 question.
Thank you. Yeah, this is joint work with Amanda Hirschi. I'll remind you what the 4-6 question was. Okay, so first let's go through some background. Okay, so as you may recall, we say two closed symplectic manifolds x1 omega 1 and x2 omega 2 are deformation equivalent if there exists a diffeomorphism from x1 to x2 such that pullback of omega 1 is connected to omega 2 is connected to omega 1 by a path of symplectic forms. And note that we have no assumptions on the cohomology classes and no assumptions on diffeomorphisms. So orientation preserving or reversing, both are fine. And then the 4-6 question, a credit to Donaldson, is that given two closed homeomorphic symplectic four manifolds, x1 omega 1 and x2 omega 2, he asked, are they diffeomorphic if and only if the product manifold x1 cross s2 and x2, and then where the symplectic form is you're just summing with the standard form on s2, if these two six manifolds are deformation equivalent in the sense that I defined before. Let's call this stabilization in this talk. This process going from four manifolds to six manifolds. So why is this true even in the smooth category? So here I would like to restrict to the simply connected four manifolds, which would be stated as a conjecture that I'll talk about on the next page. But recall by Wall that if I have two closed simply connected homeomorphic four manifolds, then they are H cobordant. And then once you stabilize, you're in the dimension 6. You're in dimension 6. And then by Smale, we have that if I have two closed simply connected, let's say six manifolds, if they're cobordant, H cobordant, then they're diffeomorphic. So at least I know x1 cross s2 and x2 cross s2 are diffeomorphic. And then I can talk about, well, given that x1 and x2 are homeomorphic, so then I can talk about whether they're deformation equivalent or not. So a bit of history of this question. Ruan showed that there exist homeomorphic but not diffeomorphic Kähler surfaces such that their stabilizations, again, in the previous sense, that you cross with P1 or S2 with the standard symplectic form, are not deformation equivalent. This is given by CP2 below 8 times and the Barlow surface. And then a bit later, he, together with Tian, stated the stabilizing conjecture when restricted to the simply connected case. And this is shown for rational, they showed the stabilizing conjecture is true for rational elliptic surfaces. Iona Parker also showed for rational elliptic surfaces using slightly different method, but they still use Gromov-Witten invariance. So a bit of a spoiler for our result, we actually only used a pretty classical invariant, which is the first Chen class. I'll talk about that later when I get into the proof. And before I go on, I would like to mention Ivan Smith's work from 2000. He showed that given n greater than 2, that there exist n symplectic forms on a simply connected four manifold whose first-Chen classes have different divisibilities. So in particular, he showed that Donaldson's question cannot be replaced by T2, and what remains, well, the original question is when you stabilize with S2. So our results, the first result is that we show that there exist infinitely many pairs of closed symplectic four manifolds, x1 omega 1 and x2 omega 2. They're diffeomorphic, pairwise diffeomorphic, but their stabilizations are not deformation equivalent. In particular, we answer the forward direction of Donaldson's 4-6 question in the negative. And another remark is that we actually give two types of examples, one type given by Smith and one given by McMullan-Tabs. Maybe any questions on the statement? And then it's a natural question to ask once you know that one stabilization is not enough to make the make your manifolds deformation equivalent. You can ask whether more copies of more stabilizations will make them deformation equivalent. And at least in our examples, we showed that you cannot stabilize them with arbitrarily many of S2 cross omega S2 with the standard symplectic form. And okay, so now I'm going to the proof strategy and give you actually the examples. So the strategy is very simple. We just want to find examples of a fixed, smooth four-manifold X that emits deformation inequivalent symplectic forms omega-1 and omega-2. And then we want to show that their stabilizations are not deformation equivalent. And as mentioned before, the invariant we're using is the orbit under diff of the first-order class associated to a symplectic form. The goal is to show that the C1s are they lie in different orbits of diff of the six-manifold. And a bit more motivation before our proof. We want to emphasize that before us, there are already examples of a closed smooth four-manifold X emitting symplectic structures whose C1 lie in different orbits of diff of X, the four-manifold. And in fact, we're using such examples. And our job is to go from 4 to 6. And we will be done if we only care about diffeomorphisms of X cross S2 that is split. So we want to constrain how an arbitrary diffeomorphism of X cross S2 can act on the second cohomology of X cross S2. This is where the first-order class lives. And this naturally leads to the following definition. Given two spaces X and Y, we let GXY denote the set of cohomology equivalences. So this maps that induce isomorphisms on cohomology. So we let GX denote the set of cohomology equivalences psi of X cross Y such that the pullback maps the second cohomology of X to itself. So this is a coolness component of H_2 of X cross Y. And then we also required projection to the first component is also a cohomology equivalence for any little y in Y. Another definition is we let G tilde XY to be the H group of homotopy equivalences. So you just replace everywhere you see cohomology with homotopy. And the great thing about our examples is that both our examples have their diffeomorphism satisfying one of these algebraic conditions. And I will tell you I promise I'll tell you the examples soon. But let's just go over the proof steps again, since now we can refine it a little bit. So the first step is to find a smooth four-manifold with symplectic forms omega-1 and omega-2, such that their C1s lie in different orbits of actually cohomology, respectively, homotopy equivalences. This is stronger than finding omega-1 and omega-2 that's only that's not related by diffeomorphism. And then we want to show that this is an algebraic condition. If the C1s of the four manifolds lie in different orbits of cohomology equivalences, respectively homotopy equivalences, then C1 of the six manifolds or symplectic forms lie in different orbits of this GXS2 or G tilde XS2 that we defined before. So this is, roughly speaking, homotopy equivalent or cohomology equivalences that preserve H_2 of the first factor. And the last step is to show that any diffeomorphism of X cross S2 in the given example, counterexample X, lies in this G of X S2 or G tilde X S2. So I hope you agree if we can show all these three things, then we'll be done. Okay, so an algebraic, so this is the second step here, which we call algebraic sufficient condition. This is not enough because we need to show any diffeo would satisfy this condition, but let's nonetheless call it a sufficient condition. Okay, so the proposition goes, let X be a closed smooth manifold with two symplectic forms omega-1 and omega-2. Let's suppose their C1s lie in different orbits of actions of cohomology or homotopy equivalences of X, H over 2 of X. Then C1 of the stabilized symplectic forms lie in different orbits of G sub X S2. So they lie in different orbits when you take product. I'll give you a simple proof. It's basically algebraic topology, and you will hopefully hopefully this is self-contained. Okay, let's suppose you have a psi being this GXS2 or respectively the tilde G, such that you pull back the six manifolds symplectic forms, the C1 of the six manifold symplectic forms to one another. Then for the class that's H defined as the Poincare dual of point or algebraic dual of S2 or C1 of the hyperplane line bundle of P1, whichever you like to think of it as, we have that psi pull back this class H is equal to H plus alpha for some alpha in H over 2 of X. So note that the coefficient in front of H is 1. And this is because, okay, we know it's plus minus 1 because psi is a cohomology equivalence. And then we also know it's plus 1 instead of minus 1 because we assume psi preserves H over 2 of X. And then once we have that, and we recall H, well, okay, we know H squared is 0. We're looking at P1. So this implies that we have this equation, which will imply 2 alpha is 0 because you're looking at the cohomology ring of X crosses 2, which is just cohomology ring of X joined H over H squared. So now by this equation 1 and the fact that C1 of P1 is 2H, we have that, okay, you just expand out equation 1, and then you get C1 omega 1 is the pullback of psi. Is a pullback of C1 omega 2. And then you want to construct a four-manifold level map, which is, you just define it by the projection, and you can show that psi, since psi star preserves H over 2 of X, psi hat star C1 equals psi star C1 equals to C1 of omega 1. And then because we're projecting and basically the cohomology of P1 is very simple, we know that psi hat is a cohomology, respectively homotopy equivalence. So we have a contradiction. Okay. So now let me, now that we finished with the algebraic sufficient condition, let me show you actually the examples. The first one is given by Ivan Smith. And this is a construction of a fiber sum of T4 with 5 copies of E1 along these tori. So Tx, Ty, Tz, and 2 copies of Tw. And we can check that Tx and Tw are symplectic, while Ty and Tz are Lagrangian. So to construct the symplectic fiber sum, you actually need to perturb the symplectic form on T1 and Tz. And actually, the choice of this perturbation gives Ivan Smith the 2 deformation classes of symplectic forms. So the statement is that the simply connected manifold Z he constructed emits 2 deformation inequivalent symplectic forms omega plus and omega minus obtained by perturbing Tz or Ty. You can also do that via the opposite orientation. And in fact, 3 divides C1 of omega plus, but not C1 of omega minus. So their C1s are different, lie in different orbits of actually cohomology equivalences. And okay, and that's our job is to just show that the six manifolds remain deformation inequivalent. And the proof idea is that we use the fact that the first Montreal class of Z cross S2 is some non-zero multiple of the Poincare dual of S2. And you can see this by Hirschi's signature theorem, because the signature of Z is non-zero, that Ivan constructed was non-zero. And then we recall that P1 is preserved by diffeomorphisms up to sign, and combining this to show that any diffeomorphism of Z cross S2 will lie in G sub X S2, and then we're done. Okay, because we satisfied the algebraic condition. And the second type of example is given by McMullan-Tabs. This is more, it's three-dimensional in nature. The four-manifold you construct is the three-manifold cross S1. So how do you construct the three-manifold? You look at this link L in T3, where the first three factors are just S1 of T3, and then the fourth component satisfies L4 equals to the homology classes of the sum of the other three. And then we consider M, which is, okay, you delete this link, and then, okay, N is actually a three-manifold we want. N is the double branch cover of T3 over L associated to the homomorphism where you map M4, which is the meridian of the fourth component, L4, to -1. And then the important thing is that N is fibered, induced from a fibration of T3 over S1. You basically just do double fiber-wise double branch cover. And then let's recall the definition of the Euler class of a fibration, N over S1. So N here can be any dimension, but let's just think of it as a three-manifold. Only depends on alpha, this cohomology class, that's the derivative of rho in H upper 1. And this is given by counting zeros of the section, generic section from your three-manifold N to the kernel of D rho, which is just tangent bundle of your foliation. Okay. Oh, yeah, maybe you find it a little weird because this is in H lower 1, but it's actually, you can just take the Poincare dual and that will be in H over 2, which is the one maybe you're familiar with. So the essential lemma we need from McMullan-Tabs is that on a three-dimensional level, there exists alpha 1 and alpha 2 induced by fibrations, rho 1 and rho 2, such that the Euler classes lie in different orbits of alt pi 1. So in particular, they lie in different orbits of homotopy equivalences. And on the four-manifold level, let's look at the three-manifold cross S1. They show that you can actually compute C1 of the associated, they show that you can first associate an S1 invariant omega to each alpha represented by the differential of a fibration, and then you can compute the C1 of this symplectic form to be the Poincare dual in X of your Euler class cross S1. The corollary is that for any homotopy equivalence phi of X, you have the push forward of E alpha 1 cross S1 is not equal to E alpha 2 cross S1, which implies that the C1s of the four-manifold symplectic forms do not pull back to each other. And then for this example, it remains to show that any diffeo of X cross S2 lies in this G tilde. So this is the space of cohomology equivalences, space of homotopy equivalences that preserves H over 2 of X, and then the projection is still to X factor is still a homotopy equivalence. And this essentially follows from the fact that X is aspherical. I won't go into more of that. And so yeah, this will just show us. So once we have that any diffeo of X cross S2 lying in this G tilde, we satisfy the algebraic condition, and then we show that this shows that the McMullan-Tabs construction also gives counterexamples. Maybe one note is that this example is actually not simply connected. You have it's an S1 cross a 3-manifold. So, but yeah, that's all. Thanks for listening.
Thank you very much, Luya. It's a very interesting talk. Are there any questions from the audience?
And can you imagine the following situation that your forms on manifold cross sphere have the same algebraic topological invariant, so the same first Chern class or whatever you wish, but there is some kind of hard invariant, like, I don't know, quantum cohomology or something, which takes into account the fact that they are different, that they are not deformation equivalent.
Yeah, so on the 6-manifold level, that was Ruan's example. He constructed 6 manifolds, which are actually the CP2 blow up 8 times and Barlow surface I was talking about, cross S1. So those 6 manifolds have the same C1s, but their Gromov-Witten invariants are different. So they're non-deformation equivalent. And as far as I know, that's probably the only example with the same C1, but same line of examples with the same C1. Of course, you can probably construct more with the same C1, but different Gromov-Witten invariants. Okay, actually take that back. There are a lot of examples like this for the 6 manifolds, but for the 4-manifold, that's the open question. Maybe that's not what you're asking, but on the 4-manifold level, we don't know example of closed 4-manifold, symplectic 4-manifold with two closed symplectic 4-manifold with the same C1, but different Gromov-Witten invariants. Sorry, maybe that wasn't your question. Is that okay?
Yes, thank you.
Maybe I have a related but different question. So what is the other what would be the other direction of the first question?
Yeah, so we're preparing some notes to say if you have the 6 manifolds, the stabilized 6 manifolds have the same Gromov-Witten invariants, then their 4-manifold Seiberg-Witten invariants are the same, except for connected sums of S2 cross S2s. Yeah, it's not as good as their diffeomorphic, but Seiberg-Wittens are kind of the only thing we know to distinguish smooth structures on 4 manifolds. So that's hopefully still an interesting result.
Very interesting. Thank you very much.
Yeah, thanks.
So if there are, okay, so are there any further questions on that? If there are no further questions, let's thank Luya again.